In DC circuits, you learned that one of the 7 causes of ionization is magnetism. So let's talk about magnets and magnetism. The history of magnetism dates back to around 600 BC, where we find mention of a material called lodestone in the work of a Greek philosopher named Thales of Miletus. The word magnet is derived from magnetite, the name of a mineral found in a place called Magnesia, which is part of Asia Minor. So what is a magnet? A magnet is a piece of ferrous material that has its component atoms so ordered that the material exhibits properties of magnetism, such as attracting other ferrous materials or aligning itself in an external magnetic field. Wait, huh? What? Did you get that? How about this? A magnet is any object that has a magnetic field around it. A magnet has at least one north pole and one south pole. And as stated, a magnet attracts ferrous materials. So what does ferrous mean? Ferrous simply means that a material is of, relating to, or containing iron. Magnets come in a large variety of shapes and sizes, including ball magnets and other various geometric shapes. Different types of magnets include permanent magnets, temporary magnets, and electromagnets. Permanent magnets are magnets that always have been and always will be a magnet. They will never not be a magnet. Temporary magnets are not permanent magnets. In other words, they will either lose their magnetic abilities over time or as soon as the original magnetic field is removed. And then there are electromagnets, which are simply magnets created by using electricity. We'll talk more about electromagnets in a few moments. Now we said that a magnet was any object that has a magnetic field around it. So let's talk about this magnetic field. What is a magnetic field? Well, that's the field you plant magnet seeds in order to grow more magnets, right? Of course not. That's silly. A magnetic field is simply the area surrounding the magnet where magnetic force is exerted. The magnetic field is made up of individual lines of magnetic force called flux. A flux line, then, is an individual line of magnetic force. The flux density is the number of flux lines in a given area. This is what determines the strength of a magnet. More flux lines means a stronger magnetic field. Fewer flux lines means a weaker magnetic field. Now that we know what a magnetic field is, let's talk about some of the properties of magnetic fields. First of all, flux lines originate in the North Pole and terminate in the South Pole. Typically, the North Pole is always color-coded as red, and the South Pole is always color-coded as blue. Next, notice that the flux lines are closer together at the poles and more widely spaced surrounding the magnet. The strength of a magnet is greatest at the poles because the flux density is greater at the poles. Also, flux lines never intersect. In other words, they never cross. So, if another magnet with its magnetic field was introduced to the original magnetic field, the flux lines of both would actually bend around both magnets, creating one larger magnetic field. And finally, magnets only stick to other magnets. Well, now wait a minute, Mr. Spiewak. That can't be true because I got all kinds of magnets stuck to my refrigerator door at home, and my refrigerator is not a magnet. All right, give me a few moments, and I'll prove that magnets only stick to other magnets. But first, let's talk a little bit about different ways we create magnetic fields. One way that we create a magnetic field is through a process known as magnetic induction. Well, now there's a word for you, induction. What does it mean? Well, induction means to induce. Well, awesome. What does that mean? Think about this. Some chemicals have warning labels on them that say, if swallowed, do what? If swallowed, induce vomiting. Or how about this? To induce labor. In both cases, induce means to make something happen. In the case of the poison, induce vomiting. Make it happen. Make yourself vomit. Get it out. In the case of induced labor, well, we're making that happen too. No matter what, that baby's coming. So what is it that we're making happen? In the case of magnetic induction, we're making magnetism happen. We're creating a magnetic field. Therefore, magnetic induction is the ability to create an opposite magnetic pole in a material as that material comes in close proximity to the original magnetic field. In other words, we're using magnets to create other magnets. One thing we must consider when trying to magnetize a material is whether or not that material can be magnetized. The characteristic that determines whether a material can be magnetized is called permeability. Permeability, to put it simply, is an idea of how well a material will accept magnetic lines of force and support the formation of a magnetic field. The higher the permeability, the easier it can be magnetized. So let's go back to 8th grade science for a few moments. How many of y'all ever magnetized a screwdriver as an experiment in 8th grade science? How did that work? Well, the screwdriver, being made of a ferrous material and having a relatively high permeability, was rubbed down the length of the screwdriver with a magnet, and it became magnetized. So how does that happen? Well, I'm glad y'all asked. You see, inside the material of the screwdriver, which is made of a ferrous material, are these unseen ideas called dipoles. These dipoles are like microscopic magnets. They have a north pole and a south pole. Now, before the screwdriver becomes magnetized, these dipoles are in complete disarray. They're all mixed up. When we run the magnet down the length of the screwdriver, that causes those dipoles to all line up so that a south pole points to an opposite north pole and a north pole points to an opposite south pole. Now that these dipoles are lined up, the screwdriver is magnetized. To demagnetize it, we can heat it really hot and or hit it really hard with a hammer several times, and this will cause the dipoles to be all messed up again. So back to your refrigerator. Since magnetic induction is magnets making other magnets, we now know that as you bring that magnet to the door of your refrigerator, which is covered with a ferrous material, these dipoles in your refrigerator door line up, creating an opposite magnetic pole in the vicinity of the magnet you're placing on the door. You have thus created a magnet of your refrigerator door. Another way to create a magnetic field is through a process called electromagnetism. Electromagnetism is quite simply using electricity to make a magnet. You see, as current flows through a conductor, a magnetic field develops around the conductor. The direction of the magnetic field, or flux, is relative to the direction of current. We can determine the direction of flux using what we call the left-hand rule. Going back to 8th grade science again, let's take that same screwdriver that we were using earlier, only this time let's wrap or coil some wire around it. We coil the wire around the screwdriver because by doing so, we concentrate our flux lines, creating a greater flux density. We'll talk more about the effects of a coiled wire in another lesson. The more times we coil the wire around the screwdriver, the stronger we can make our magnetic field. Once we have the wire coiled around the screwdriver, we connect each end of the wire to the two poles of a battery or some other current source. One end of the wire to the positive pole of the source, the other end of the wire to the negative pole of the source. As soon as the wire is connected to the source and current is flowing through the wire, the screwdriver is now acting like a magnet and will attract other ferrous objects. Factors that affect the strength of our electromagnet are the number of turns, or how many times the conductor is coiled around whatever we're trying to magnetize, and the amount of current. More current produces a stronger magnetic field. Electromagnets are considered to be better than permanent magnets. Why? Because of the ability to control the magnetic field. We can turn it on or off, or make it stronger or weaker. It's all about control. So how about it? Can you come up with some real-world applications for electromagnets?